Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Now, Galois theory is a general principle that you find in pure mathematics. And to illustrate this, I want to show you in this video how the Galois correspondence occurs in topology and is in fact dual to the Galois theory that you see in fields. Okay, so we've seen the Galois group and how it can be defined for coverings or covering maps. And now what we want to do to set up our Galois correspondence is to have the analog of intermediate fields. So remember, the notion of a covering map is supposed to be the topological analog of a field extension. So now we want to have an analog of an intermediate field, and that's the notion of an intermediate cover. Okay, so let's go to our setting that we work with when we're talking about covering maps, and that's going to be in the setting of connected, locally path-connected topological spaces, which I denote with the CL0 top here for that category. Okay, so remember, such spaces are automatically path-connected, and let pi from x to y be a covering map. Okay, so here we have x to y like that. So what's an intermediate cover? So if you have an intermediate field, you have a field extension, you have a subfield of another field, that's some field that gets sandwiched in between. So basically we want to factorize this map here with something in the middle, an intermediate topological space. Okay, so that's going to be our intermediate cover. It's going to be essentially a diagram like this with certain special properties. Okay, so what's the commutative diagram? Okay, so it's a factorization of pi. So we have a topological space here Z and map phi and psi continuous, so that pi equals psi phi. You do phi and then psi, so that's commutative diagram. And you want this to be nice in the following sense. Firstly, this map here has to be a covering map from Z to Y. The psi is a covering map. And the other thing that you want is this phi to be surjective. Okay, so surjectivity of phi. So you may think the definition is a little bit asymmetric at the moment, but it turns out that it's quite easy to see that in this special case, and this is the proposition part of this statement here, that phi is also a covering map. So in fact, both these are covering maps. Okay, so let's just give a rough explanation, geometric sort of explanation why you expect this result to be true, that a phi is automatically a covering map. Okay, it's quite easy to prove, and this is the basic idea, so you should be able to come up with the proper proof once you've seen this picture. Okay, so remember, what does it mean for x to y to be a covering map? That means that above every point here, right, you can take a small enough neighborhood such that its inverse image here will be a union, a disjoint union of open sets which map homeomorphically onto here under this pi map. So it breaks up into basically a copy of them. Okay, so maybe there are 1, 2, 3, 4 copies. Okay, and each of these maps homeomorphically onto that one there. Now also this psi is going to be a covering map, so this also splits up. The inverse image of this open set inside here splits up as a union of things, there may be 2 of them. Okay, and each of them map homeomorphically onto that one there. And I hope you can kind of see what should happen in this picture. Okay, so this is a surjective map, so the inverse images of these 2 will be all of these 4 that you see here. So what must happen, so well, I guess you can make this small enough. Remember, you're locally path connected, so also path connected because you're connected as well. You can choose this to be small enough to be connected if you like. And so when you take the inverse image, these are just like path components essentially. And these are path components. And what you can do is you can say, well, in this case here, you can look at the inverse image of that, and what must that be? Just from the fact that the inverse image of this is this, you'll see that it has to be just a number of these path components. Okay, and so each of these path components, of course, map homeomorphically onto this, and hence they'll map homeomorphically onto one of these 2. Okay, so that's basically the proof. Okay, it takes a little bit of thought to see that all the statements that I made here are actually true, but that's the basic idea, and I hope you can believe that that certainly is what you would expect. Okay, so the situation here is actually quite different from what you see in field theory. Okay, there's a slight subtlety that's involved here. So the slight subtlety that's involved here is that whereas before, okay, so firstly there's some duality that's involved. So normally you talk about subfields. Okay, so you have an injection. Okay, that's your That's what's happening in the field situation. Here you have a surjection. That's your covering map, which is a surjection. Okay, and then what you do is that whereas in the case of fields you have a fixed intermediate field, so that's something that's a sub-object. Here you have a quotient object, or not quite a quotient object here, because this is not strictly speaking a quotient object. It can be mapped to something which is kind of floating around. It can be anything. In particular, you can replace this z with something that's homeomorphic, and then you'll have to modify phi and psi appropriately, okay, with that homeomorphism, and that will give you something isomorphic. Okay, so there's a little bit more floppiness in the definition here. And if you want to get rid of that floppiness, we'll have this little lemma here. Okay, so what's this little lemma? So this is also a good fact to know. Okay, so let pi from x to y be a covering map. So it turns out that every covering map you can think of as a quotient map. Okay, in the following sense. So let this be a covering map. Then you can define an equivalence relation on x. If you want to form a quotient of x, you need an equivalence relation on there to form a topological quotient. And of course you want to recover y, so the natural thing to do is that, well, how do you get that? Well, equivalence relations are also an equivalent concept to a partition. So we just need to partition x, okay, in such a way that each of the subsets in the partition, which form the partition, correspond to points in y. And of course the easiest way to do that is, since this is surjective, x is just the inverse image of all these fibers, all these pi inverse of all these points on y. Okay, and that will allow you to put an equivalence relation on here. Okay, so just to spell it out, when are two elements of x equivalent? If when you map them down to y, they are the same point. Okay, so that's the equivalence class. Okay, pi inverse of y is an equivalence class. Okay, so certainly when you do this, hopefully you can see that easily enough that this pi will induce a map from this quotient set x modulo this equivalence relation with y. Okay, and of course by the universal property of quotient maps, okay, this will be a continuous map. And the key point is that in this particular case, because it's a covering map, it will also be an homeomorphism. Okay, so really you can think of every covering map as being, you can replace this y with this quotient. So it is a type of quotient map. Okay, and I don't want to go through too much why this is true, but the explanation is as follows. Okay, so firstly, because pi is a covering map, it's a local homeomorphism. So that's something that we saw last time, and you can see quite easily in this picture here why this ought to be true. So if it's a local homeomorphism, that implies that it's open. Okay, so basically the main thing here is that you have a continuous bijection, and you want to show it's a homeomorphism, so we want to show it's open. Well, pi is open. Okay, so if you go from here to here, it's open. And so what you want to do is you want to conclude that this map is open. Well, pi open implies that pi bar is open. And the reason why is that, well, to check that it's open, you want to look at the image of an open set here. Well, you take an open set here, you pull it back, you take the inverse image via the quotient up to x, and that's an open set. And since pi is open, the image of that open, which is also the image of the open here, by surjectivity of this map, this pi bars are also open. Okay, so hopefully your point set topology is good enough that you can work that out, okay, but it's not difficult. And the main thing to see from this lemma is the fact that, well, if you want in this definition, we don't need to really consider all intermediate covers, but this is the useful form of our notion. You can look just at replacing z with only quotients of x. Okay, so that's very similar to the situation we had with fields. You just look at subfields of the big field. Okay, so you can also just look at quotients of that. Okay, so the theory is a little bit more subtle. Okay, in topology there are some conditions, and I'll talk a little bit more about this later. So one of the notions that we need here is something called simply connected, and it's to do with studying topology in a homotopy sort of setting. I'll talk about homotopy later, but for the moment we just need this very simple notion here. Okay, so a path connected space X is called simply connected if every loop based at some point X, or any point X, contracts to a constant loop at X. Okay, that's quite a mouthful, so let's just see what's going on here. So let's suppose we have this cylinder is our x, okay, so we pick some point x, any arbitrary one x, and we consider a loop based at x. So what's a loop based at x? It's just something like this. Okay, I want to think of something like that. Okay, that's my loop based at x. So you can think of it as a little rubber band, and it starts here and it goes off to here. And now it should contract to a constant loop at x. So let's see how this contracts to a constant loop of x. And the way to think of this is you can think of this as something that's dynamic. Okay, that's an animation. So you can shrink it down until it becomes a single point. Okay, you can. Here's one part, and then you can make it smaller and smaller and smaller and smaller until you get to the constant loop at x. Okay. Now it turns out that this cylinder is not simply connected, because for this to be true, you need this to hold, this ability to contract to the constant loop. You need this to be true for every loop based at x. Now if I picked a loop that goes around the cylinder instead, so maybe it goes down like this, and then back up. For example, it just goes around this pen, then it doesn't matter how you move it along the cylinder, you won't be able to squash it down to the constant loop at x, okay? Okay, so that's what's happening, it's this cylinder here. Okay, so let's just go through the formal definition of what's involved in here. It involves the notion of a homotopy we'll talk more about later. So the first thing is we need to define a loop, and the loop is fairly simple because it looks topologically like a circle. So we start with the circle, S1, and the way we'll express this circle this time is we'll look at it as a quotient of the unit interval where you identify the two ends, 0 and 1, so they've been identified. And in this case, a loop at some x, an amount of x, it's just a continuous map. The actual loop is a continuous map from this circle S1 to x. And it's at x. What does it mean to be at x? Well, there's a special point in here. The way I wrote it, the endpoints are special, okay, 0, 1. And f at this equivalence class here, 0, 1, is going to be at x. Okay, so there is a distinguished point on this S1. Okay, and what does it mean to contract this loop? Okay, so what we want to do is we want to think of this as a time-lapse sort of picture. And at time t equals 0, you get this loop. Okay, so we're going to put t equals 0 there. And as you go from time t equals 0, we dynamically shrink it down until we get the constant. So we get something smaller and smaller and smaller and smaller. Maybe at time t equals half, for example, you get something that's this size. And then get smaller and smaller and smaller until time equals 0, you just get the point. Time equals 0. Okay. So what we're going to do is to have all these different loops, we need a loop for each time from 0 to 1. So the time vary from 0 to 1. And for each of these, we're going to have a continuous map from S1 to X. And of course, the whole thing should be, all these loops should be compatible. So what we're going to do is we're going to look at the product space S1 cross 0, 1. And we're going to look at a continuous map from F tilde from S1 cross 0, 1 to X. That's going to be my contraction, okay? That's the starting point. And it has to be contraction from, firstly, the loop that we had, this loop F here, to the constant loop at X. Okay, so let's put those information in A, B, and C here, these conditions. Okay, so firstly at time t equals 0, so there's a 0 here. F tilde of Z is just the original loop. Okay, so this is now just a function of S1, and it's just my original f of z. Okay, what about at time t equals 1? Okay, that's not a 0 there. That should be a 1, sorry. So time t equals 1. Time t equals 1, f tilde of z is always, for every point on the circle, every z on the circle, it's going to be x. It just stays there. Okay, and finally, all of these, it doesn't matter at what time, okay, for every t inside here, you have to have a loop at x. So that means the endpoints for every time has to be x for all t. And you have this, okay, that's called a contraction to the constant loop at x. So that means for every loop, this continuous function, you can basically what's called lift this to a continuous function from S1 to cross 0, 1 to x, which with these properties. Okay, so lifting means that, well, it starts here like this, okay? So that's the what you see there, and it also has these properties. Okay, so now we can move on to describe the actual Galois correspondence in topology. Now, we have to restrict the category we're working with a little bit more. Okay, instead of looking at CL0 top, we look at CL1 top. And what's that? So now we look at a subcategory of the category of connected and locally path-connected topological spaces. So now we look at these topological spaces X, which furthermore have this extra condition, which is called semi-locally simply connected. And what does that mean? That just means that X has an open cover U alpha, such that these U alphas are simply connected. Okay. So I guess I forgot to give you some examples of what the things are simply connected. If you're in Euclidean space, okay, or in a Euclidean ball, okay, any loop that you have, you can just shrink it down to a point, okay. So that's easy enough. And the way you can do that is that you can basically just scale everything down to a point. Okay, so Euclidean space, this is true. So the good examples of topological spaces for which this is true is if you have an open cover where each of these U alphas is a Euclidean ball. Okay, that's an example. So if it's a Euclidean ball, so that's so if you have a connected manifold, topological manifold, then you're in this situation here. Okay, so that's probably a good example to keep in mind. Okay, so in that case, remember you have a cover by Euclidean spaces or open balls in Euclidean space. So it is semi-locally simply connected, and of course you know it's locally path connected. And if the manifold is connected, then you'll have all the conditions that you need. Okay, so I've mentioned a slight subtlety with working with intermediate covers before, so let me just kind of make sure that we know how to get around it. Okay, so we need the notion of an isomorphism of intermediate covers. Okay, so suppose you have two intermediate covers of x to y, so x goes to z1 to y, and x goes to, that's a z2 to y. Okay, so you've got two intermediate covers, and what's an isomorphism? I hope you can guess what that is. It's going to be a homeomorphism from Z1 to Z2 such that this diagram commutes. So it doesn't matter whether you go this way or this way. Okay, so this one is the same as this, and this way is the same as that. Okay, that's a homeomorphism. Okay, so now we can state the Galois correspondence in this situation here. So firstly, let's remind ourselves what was the Galois correspondence in field theory. Okay, so if you have some Galois extension there, okay, you have a Galois field extension on one side, then you can look at its Galois group on the other side, and then the subgroups on the group side are in bijection with the intermediate fields on the other side. And in fact, these are posets on both sides, and there's an inclusion reversing bijection between these two posets. Okay, so that's rather nice. And in this case, we have the same deal. Okay, so so the setup though, I'll write slightly differently. So one of the easiest ways to get a Galois extension, in fact they all occur like this, is you start with a field and a group of automorphisms of that field, okay, which is finite, and you look at the fixed field. Okay, so that will give you some sort of Galois extension. So that's the version that we'll look at here. We're going to start with some x, which is some topological space in CL1 top. So it is connected, locally path connected, and semi-locally simply connected. We're going to let G be a group, okay, which acts freely and discretely on this x. Okay, and once you have that situation, you can map from x to the quotient x mod G, which I'll call y, apart from x to y. And that's going to be, as we saw before, that's going to be a covering map. So here we have a covering map. You have a covering map, so you can talk on the one hand about intermediate covers, and we want to just look at them modular isomorphism. And that's the same essentially as looking at intermediate covers by this lemma here, where this z is always just a quotient of the top one, x. If you like, you can do that if you don't want to see this modular isomorphism here. And that's in bijection with H mod the subgroups H of G. Okay, so that's rather nice that you now have a Galois correspondence in topology, which tells you essentially one way to think about it. Usually the group side is easier. Okay, so once you just study this algebra, which is something which you can calculate easily, you can say a lot about the topology. Okay, so let's see how that works. Okay, so how does this work? By the way, there's also this there's a poset structure on both of these. Okay, I haven't put the poset structure on intermediate covers, but perhaps you can guess what that is. And there is an analog of the fact that in the field theory version, you have an inclusion reversing bijection. Okay, I'll let you think about what that would be. Okay, so firstly, let's just see what you have here. So here I have a subgroup. Let's see what is the corresponding intermediate cover. Okay, so what do I want to factorize? You have a map from here, x to, eventually it will go to x mod g, which is y. And I want to sandwich something in between. So whereas before, when we looked at the Galois correspondence in field theory, you looked at the fixed field. So I want to use this h here, but I don't want to look at the fixed point set. Instead, I want to look at the quotient by h. Okay, you just look at the quotient by h. So this is a set of h orbits. And of course, every h orbit is contained inside a g orbit because h is a subgroup of g. So you can send the h orbit to the corresponding g orbit containing it, and that's the map here. Okay, and so you can see you split up this map from x to y, okay, into a pair of continuous maps like that. And actually, this will be an intermediate cover. Okay, so that's rather nice that you have that situation here. Okay, so what about the map going the other way? So you want to add a subgroup of H if you're given, or G rather, if you're given an intermediate cover like this. And how do you do that? So suppose you've given that intermediate cover, then what is this here? So remember, another way to think about G, okay, in this setup here, is it's the Galois group of X over Y. It's the set of all homeomorphisms of X to itself, automorphisms of X, which preserve the map from X to Y. So now you want just some of those homeomorphisms, okay? So which ones do you want? You want a subgroup of that, and it turns out what you want is just a Galois group of X over Z. And it's not hard to see that, well, if you have an element inside here, so it's a homeomorphism, an automorphism X with respect to this map, then since you're adding something here, it will also respect that map. Okay. So remember, this consists of what are the elements inside here? Okay, so maybe you have this is pi z. Okay, the elements inside here are phi, inside here. Phi is such that it doesn't matter whether we do this first and then the pi of z. That's the same as if you do the just the pi of z. So I guess to check that such an element, phi, is also in the Galois group of x to z, you need to say that it's this phi. If you do that first, it's the same if you go all the way down. But if you just compose both of these with this quotient, this map here, you get that equation holds. And so each of the elements inside here is indeed an element of the Galois group of x over y and hence of g. Okay, and that shows you that this is a well-defined map, okay, over in this direction, and in fact it will turn out that this gives you inverse bijections. And there you have it, the Galois correspondence in topology. I hope you enjoyed this adventure in pure mathematics.